No way. My Adobe thing just shut down in the last 2 seconds. Okay, that's fun. Well, E for effort, I think it says. You can't give A's for effort, Katrina. Because it didn't succeed. Alright, I'm just staying over here because for some reason it randomly shut down on me while I got there. Instead of an A for success, it's an F for success. Poor Katrina. Alright, kiddo, section 6.1. It was all about areas between curves. So, I'm over here at my computer. You guys help me out. What was the... Ooh, that's way too zoomed in. There we go. What was the first even?
26.
26. Oh, that makes more sense. Sorry, my screen is spazzing, so I'm having issues. 6.1, number 6. That didn't really help. There he is. You guys didn't even have to solve him? Oh my goodness. 2 times the integral 0 to 1 of x minus 1 cubed minus x minus 1. Now wait a minute, that's weird. Why is there a 2 in front? Because there's 2 of them? I don't have the problem memorized. You guys okay with number 6? Ah, that's what I figured. That's what I was asking. Question, what bounds did you guys get? If I was to cover up the 2, what bounds did you guys get? 0 to 1 and then 1 to 2. Yeah. 0 to 1 and then 1 to 2. Question, did those 2 areas, because you were supposed to write the problem down, did those 2 areas look exactly the same? I know we're tired, kiddos, but you were supposed to write this down. I don't know why we're acting like we have no clue what's going on. My guess is it's something like the even property. Remember how the even property, they can shorten the formula, they can shorten the work, and they can just say double? So, in number 6, the picture that you should have drawn, because it was the problem, they are the exact same area. So instead of having to solve 2 different integrals and orient it differently and do 2 different bounds, 0 to 1 and then 1 to 2, and changing the orientation, they said, forget all that work, just do one of them and double it. So what did they do? One of them and double it. Okay? All right, what's number next even? 18. All right, the picture for number 18 is given. In order to be able to do the area between, we had to find the intersections. Algebraically, it's possible with factoring. The intersections are both -3 and 2. You have x's and y's. For letter A, you're just trying to find the area. So use those intersections, -3 and 2. If you have the picture, which either they had you get or they expected you to get, or if you just used absolute values, you could have done one function minus the other. The line is on top, so he went first, minus the bottom. That's why it's all in terms of dx. Or I should say in terms of x. That final answer is 125/6. Letter B says, try it with respect to y. Now, kiddos, we did something like this in our examples on Friday. It was this one. We solved this problem 2 different ways with respect to x and with respect to y. That's what's going on in this problem. They're having you solve it 2 different ways. The top-bottom was way easier. Line's always on top, parabola's always on bottom. But for letter B, it says go right, left. Ugh. Why is that a struggle?
You have to split it.
You have to split it because if you were to go right, left,
You only make it up to this.
all the way up to here, what's on right is the parabola, what's on left is the parabola, and then once you get past that, from 0 to 2, once you go from 2 to, no, sorry, 0 to 4.
4 to 9.
0 to 4. That's from y equals 0 to y equals 4, and then from y equals 4 to
1 equals 9.
y equals 9. The line's on right, and the parabola's on left.
Yep.
And you have to use your functions as they gave them to you. So I think they gave you y equals x squared. So then x equals positive root y over there. X equals negative root y over here. Those are the 2 different branches. So you have a positive root y here, a negative root y there. But when you subtract them, it just ends up being double, or 2 root y. So that's from 0 to 4 and from 4 to 9. The lines on the right, which you have to solve for x, you end up with 6 minus y. The parabolas on the left, so plus root y. Oh, they put a bracket in? Something should be in here. Typo, they didn't put in their other bracket. There we go. So it's possible both ways, you get the same answer of 125 over 6. However, long story short of all that they asked you to do on this problem, is it easier to do top bottom or right left? Top bottom in this one. Not always, but top bottom on this one. Final answer 125 over 6, and they say, hey, yeah, top bottom's way easier. Number next one.
22.
Oh, he's over there. Solving for points of intersection, you got 0 to 4. You go ahead and throw it in an integral. Your final answer should be 32/3. Positive 32/3. If you got a negative, it just meant that you oriented it wrong. And what were you supposed to do at the end? Fail safe? Absolute value. So if you got a negative, just make it a positive. But double check that you did it right. Remember next one. 40? 40 even, right?
Yeah.
Trigonometric stuff, that's gross. I know.
It was.
But you can still orient it right, and you still have two curves that you're subtracting, then you can still integrate with u substitution. Don't forget u is 2x, du is 2. You have to divide by 2, multiply by 1/2. Plug it in. Final answer is 1.299. 3 root 3 over 4. Much nicer. Much nicer. Real quick, on number 40, did you guys have to find your own bounds?
No.
Oh, go team. How could you have found your own bounds? Set them equal to each other, exactly, and then solving. But cosine 2x, ew, gross. What would you have done with that?
You have to do 2u or u.
But how would you solve cosine 2x is equal to sine of x? I know that they were nice. I was nice by giving a problem. You didn't have to choose the bounds. How would you have solved this, though? It's a pre-cal problem.
You do 2x equals cosine negative.
Isn't there a value? It's like 1. It's like
1
cosine
minus
sine. 1 minus 2 sine.
Is this in our forever card somewhere?
Yeah. No, I don't think so.
Yeah, it is.
Did we just do double angle sine?
That's like the first.
I think we did double angle
It
sine
did.
and
It's like
double
the
angle
first
cosine.
forever card.
You would have to end up getting your 2 sine squared of x
Factor.
plus sine of x minus 1.
How would you do that?
Factor?
Yeah.
There's only one way to make 2, only one way to make 1, and you have to do a positive. So then sine is going to equal 1/2, or sine is going to equal -1. Sine equals -1 at -pi/2. And sine equals 1/2 in the first quadrant at -6. Now, there are infinitely many more, which is why it was nice they gave them to you. Because if this keeps going, guess what it's going to do again? Intersect, and again, intersect, and again, intersect. So it's nice they told us only look there. Okay. Any more evens? 82? Okay.
Yeah.
And nothing in between, right? Multiple choicey ones, right? Final answer is C. I'll zoom out just a little bit. Final answer is C. I just said equal to each other. You end up with y is equal to -1 and 2. So they went ahead and used those as their bounds. They did right minus left because everything was in terms of y, and the picture looked like a right-left picture. Final answer is 9/2 or C. Did I give you another even, or was that it?
That's it.
Dun, 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 dun. All right. We graded, but that does not mean just because we looked at it together in class for like 5 minutes, it doesn't mean you totally understand it. If you have a test coming, if you have questions, come find me. I should have a student council meeting during lunch.
Yeah.
You can still try, because it got canceled last week. But-
Test.
Never mind, we still have our student council meeting. However, after school today, tomorrow during lunch after school, Wednesday, 0 period, etc. Ooh, one logistic I forgot. That's on the backboard. I am collecting money for shirts and sweatshirts this Wednesday and Thursday so we can pay our school back who's paying for our purchase order. And we should have them next week. Here we go. What do you guys see? You see food.
Shape.
You see shapes. You see what types of objects?
Edible.
Okay, edible objects. That wasn't exactly what I was going for. But keep going.
Shapes.
Not objects.
Someone said volume. Why are you talking about volume?
Curves.
Because there's cross sections.
Okay, so there are curves. Number one, these aren't just like rectangular solids and cylindrical prisms. Okay, these are somewhat non-geometric. I mean, the orange is pretty close to geometric. The lime, I suppose, would be in the tomato. These ones are non-geometric shapes in the sense of non-basic geometric shapes. These are all three-dimensional, right? However, what part of a bigger three-dimensional object am I trying to show you?
Earth.
What? What part of a three-dimensional? Am I showing you the
Oh,
entire
goes
loaf? Am I
back.
showing you the entire piece of watermelon? Am I showing you the entire lime, the entire tomato, the entire orange? No. I'm showing you a piece of it, but let's be snazzier, a slice of it. Right? What's in common? They've all been sliced. Now, hold on. Do you want to hear the snazzy term for slices?
Cross-section.
Cross sections.
Whoa.
Now, I'm not going on chop right now, but slices, cross sections. Okay? Now, what's the dilemma with how much I can actually represent a slice to you? What's the problem anytime I try to mathematically represent a slice? Is a slice supposed to be two-dimensional or three-dimensional? Well, these are all three-dimensional, true? But in math, when we show slices, when we show planes, are they two-dimensional or are they three-dimensional? Two-dimensional. So the struggle is what we're going to learn today. We have to think about three-dimensional slices, but we need them infinitesimally thin. We need them infinitesimally thin, and you'll see why. Because if they're not infinitesimally thin, unlike these ones up here, if they're not infinitesimally thin, we won't have an exact volume, we'll just have an approximate one. But here's the idea. If you put slices together, what do you get? The whole. If you put all the slices together, you get the whole. Or if you want to think about what shape comprises the whole, you can take a slice, right? Okay, here we go. What have you guys written down so far? Find the volumes of three-dimensional, that's coming up. Three-dimensional figures using integration, helpful for those outside of geometry, like a loaf of bread. Although that's not one of the most common ones, but just trying to show you he's not rectangular. Struggle. How will we know the volume of a loaf of bread? We break it down and then we figure out the volume of a slice and then we add all the slices together. But we don't want to do that by hand. That sounds kind of messy, like Riemann sum sort of things. Maybe integration can help us, and it can. Cross sections are slices of three-dimensional figures. If you guys already wrote that, maybe this makes a little more sense. Through integration, we can combine all the areas of the slices to find the volume. Wait. You can add areas to find volumes? Does that make sense?
Yeah.
So, hold on. If we were doing geometry sort of things, let me get back to my other notes. There we go. If we were doing geometry sort of things, let me add a page real quick. This is saying add areas to find volumes. Have we ever done this in geometry before? Question. Oops, I need to import a page below. What is the area of this guy? Base times height, right? We can find his area. Base times height. Or maybe a little bit better. Can I just do length times width? Is that okay?
Yeah.
Okay. What kind of shape is this?
Rectangle.
It's a rectangle. True. And I just found the area, which is what type of measurement? One-dimensional, two-dimensional, three-dimensional? Two-dimensional. Infinitesimally thin rectangle. How do we find volume of the following? Length times width times height. Length times width times height. Yeah, it is length times width times height. Can we pretend this thing is fallen down so the height is like over here? Is that okay?
Yeah.
Okay. So we have length down here, we have width over here, and we have height up here. What does this formula actually do?
It's saying you add all of this first. Right? H amount of times.
You're accumulating all of the two-dimensional slices through the third dimension. You're accumulating all the two-dimensional slices through the third dimension. And when you accumulate all of those two-dimensional slices and you put them all together, what are you finding?
The
The volume. So in a way we've been doing this, and guys, let me give you another example. What if I was to ask you something like, hey, what shape is, let me change the color just for the heck of it. What shape is this one? Well, he's on the ground. We'll say he's a circle. We'll say he's a circle, okay? How do we find his area? Pi r squared. Question. What do we do once it's time for us to find this guy's, this guy's,
the
okay.
knife is squishy.
It doesn't like making another circle for me for some reason. I'll have to do it myself. Okay. What happens when we have to find this guy?
We're taking the circumference.
Taking all the circle pi squared.
We take the area
the
of
volume,
this
sorry.
dude, and the area of that dude is pi r squared, right? And how do we find the volume of the cylinder?
Times height.
Times height. What are we doing?
Just adding all the circles. H amount.
We're accumulating all the little circles in between. We're accumulating all of them. Accumulating them through what? Through the height. So area, pi r squared, volume, pi r squared h up above. Area, length times width, volume, length times width times height. We are accumulating slices. You just probably didn't ever think of it that way before. So let's go ahead and go back to what we were talking about, the cross-sectional slicing thing. Let me go find the link that I opened. And let's get a few more ideas of accumulating, but what else can we accumulate besides cylinders and squares? We can accumulate to get something like, what? No. Are you not up anymore? This is lame.
It's just a lot of people just
Just zoom in on it.
Alright, it's gonna be like awkwardly probably pixelated. Okay. Some Calc kids that finish Calc a whole lot faster than we do get to do cool projects. Simulating this whole idea of volume by cross sections. And they can find volumes of, hey, can anybody tell what the cross sections are of this big old like raindroppy thing? No, golden egg. I don't even know what's going on. The golden egg, can you tell what the slices are? What are the slices that have been accumulated here? Circles. They're circles. Guys, could the people making this project, could they actually figure out the width of their circles and then the radius of their circles and then figure out the volumes of each of those little tiny cylindrical shells and add them all together? Yes. And could they approximate the volume of their golden egg? Yes. This guy, same dealio. They could actually measure the width of this, and they could do the length and the width, and then they have like the height and a little depth. And they could find the volume of each of these, and they could add them all together and approximate the volume of this irregular shape. How about this vase? Can you guys tell what the... actually, I think it's taped against the board, so I think they're semicircles. So I think it's only popping out one direction. Semicircles, they could do the area, that's the volume approximated with all their little slices. Same thing here, they made a fishy with semicircles. There's a little fishy and a little tail. There's a moon with, I think those are rectangles, look like rectangles. An accumulation of rectangular slices. I have no idea what that is, I can't tell. That's an ice cream cone, I think it's the cone. I think they're right triangles they were doing in that one. Here's another with the raindrop that's like suspended. Isn't that cool? With, once again, little baby cylinders. They do a snowman.
Sure.
Here's more, I think these are isosceles triangles with a shark. Anyway, the idea is if you can figure out, using geometric slices, if you can figure out the volumes of those geometric slices and accumulate them, maybe you can make non-geometric shapes, like a vase, or like a sinusoidal three-dimensional curve, or like a fish or a shark, right? So, let's come back. Let me show you some more mathematical ones. Those were just like CalcABs trying to make different. Oh, that's not helpful. This is just not a good day for our network. Yeah, that's cool. All right, let's just keep going. No idea what's going on. Here's some more mathematical things that are going on. Let me zoom ahead this way. All right. Now, these ones are actually known basic geometric figures, right? These are known basic geometric figures. You guys don't actually have to write these if you don't want to. But I'm trying to show you what I was just showing you with the rectangular solid and then with the right cylinder. How you can think of a right cylinder as being comprised of infinitely many, very, very thin, but infinitely many two-dimensional cross-sections put together. Same thing with a pyramid. You can think of them as having infinitely many cross-sections of squares put together. They're just showing one representative one, but if we put all of them together, and I'm only showing a few, once again, I'm showing a finite number, but if we were able to make this infinitesimally thin, put them all together. Long story short is this idea down here that we're going to make a forever card. Don't stress. We're going to make it a forever card. But volume can be found by accumulating two-dimensional areas. However, here's the struggle. If two-dimensional areas have no depth, then how can you add them together to suddenly have a depth?
Use that equal to the universal unit.
Well, even with the universal unit, we can't really take something with no depth, add them all together, and then get it to have depth.
Or just pretend.
However, integration was based upon the fact that if you do accumulate infinitesimally thin or approaching the second dimension figures, rectangles that are getting infinitesimally thin to kind of approach lines accumulating, or slices that are actually little cylinders or little rectangular solids that actually have depth like the slices of bread that we saw. The integral says, I'll approach infinitely thin and I'll accumulate them. Bless you, bless you. There's one of the huge debates, bless you, of calculus and integration when it was first brought up. It's actually the religious, I think it was these monks, that were like, you can't make something out of nothing. Interesting.
Yes, we can.
But integration says, yes, you can. But it's not that we're necessarily making something out of nothing. We're using limits. We're approaching nothing. And then we're accumulating them. So let's go ahead and get some actual solid stuff down. First of all, before I give you the formulas, slicing, slices, cross-sections. The way the slices or the orientation of the slices determines whether with respect to x or with respect to y. The orientation of the slices determines whether integrating with respect to x or with respect to y. So as you can tell, now we're dealing with the third dimension. So we have an x-axis, we have a y-axis, and we have a z-axis. And if you can notice, whenever we're slicing, we always think about perpendicular to, not parallel, perpendicular to. If you had a knife and if you were slicing right where that little representative red slice is in the middle of this figure, are you slicing perpendicular to the x or perpendicular to the y? You guys see it? Isn't that perpendicular to the x? So since it is perpendicular to the x, we're going to actually make this a dx integral. It's going to be with respect to x. And the reason being is we can't physically accumulate infinitesimally thin. So what we're going to do is we're going to represent something that does have these slices that do have just a little bit of depth. And with an integral, the integral is going to make it infinitesimally thin for us to make it precise. We're going to have it be just a little bit, or have just a little bit of depth, and we need the integral to make them infinitesimally thin. That little bit of depth we represent as dx. Here's where you kind of build upon your understanding of the differential. The differential is some sort of measurement. Like with normal integration, area under the curve, the dx was the base of the little rectangles that we put inside the integral base 10 height. by hand, we could do a finite number. The integral can do infinitely many because it makes that differential infinitesimal thin. So we make the depth dx. We multiply that depth by the area, then we have all these little volumes, and we add them all up, and the integral makes them infinitesimally thin and precise. Long story short, when you slice perpendicular to the x-axis, we're going to be representing our volume integral with dx. When we slice perpendicular to the y-axis, this is a little harder because the y-axis is way over here, but if you still notice with the slicing, where would the depth be on this guy? The depth would be a vertical component, which would be a dy. The depth would be vertical, which would be dy. So whenever we slice perpendicular to the y-axis, even though it might be removed from the y-axis, whenever we slice perpendicular to the y-axis, if we were to have our knife keep going, it would come down this way, which would be perpendicular to the y-axis. Then we're going to have dy. If you guys want to think about it, you can kind of think about like a bagel slicer, sort of. Anybody ever cut a bagel with one of those bagel slicers where you have like a hollow, and then the knife goes in and it has like two different sides to it? Nope, no one's worked at a coffee shop. Never mind. Think about a knife that has two blades and a hollow space in between, like a slice of bread. You don't cut twice, you cut once and you get both sides. Huh? Yeah, kind of like a toaster in the sense that it has like a hollow. Just think of that's what you're slicing. Okay, so with that, Sarah. Because the integral takes this, and what would be kind of fragmented, like you see the student projects over here, it's fragmented, right? That's not precise because it's an actual finite number put together. Once we assign that depth in our notes to dy or dx and integrate, it can accumulate these infinitely many so they get thin and then they approach the actual perfect curve. Does that make sense? Cool. Good question. Okay, let's get this forever card. So we've already talked about the main idea. I don't know if you guys necessarily need to write it again, but we can get three-dimensional figures generated by accumulating their cross-sections. Or we can find the volume of a three-dimensional figure by accumulating their cross-sections. And that's going to look like in an integral that volume will equal, if it's in terms of x, from x1 to x2 from bounds, x1 to x2, we're going to use an area formula. Now the area formulas are going to change because, as you guys notice, we can have different areas. We can have semicircles, we can have actual circles, we can have squares, we can have right triangles. So we're going to accumulate using an integral where volume is going to come out of us putting in the area of the cross section in terms of x or in terms of y, multiplying by dx or dy to get some depth to it, and the integral says, no problem, I can take it, I can work with that, and I can solve for it precisely. So by capital A, I just mean the geometry formula for, or the area of the cross-section. If you guys want to make it a little more precise, we could go ahead and put it down below. Area of the cross sections or the slices. I'm going to put that in parentheses, but I am going to include that in your forever card. Did you say? Oh, that's cool. Underneath the box, area of cross sections. And I believe this is forever number 47? Okay, forever number 47. I? There we go. Forever number 47. Now, I know class is almost done, so we're not going to be able to solve any of these. But what I do want to show you is where we are going with this, because this is actually the end of our 4-7. This is the end of our 4-7. Where we're going with this is something called solids of revolution. And this is where our 6-2 starts. We actually start at the end, so I think it builds upon better. My question to you is, in looking at this solid of revolution, which if you want to think about paraboloids and hyperboloids from last year, this solid is formed by this region right here being rotated around an axis. But my question to you is, with this rotation, whenever you rotate something, what are its cross sections, what are its slices going to have as their area? What shape is their slice? A circle. And what area formula are we going to use if we have circular cross sections? Pi r squared. And so this new forever card that we're going to see tomorrow, does anybody see pi r squared in there?
Yep.
I thought pi r round. Anyway, kiddos, pi day tomorrow. I'll see you later, alligators. I think it's chapel day, right?
Yeah.
Did everyone just get randomly out early? Get out of here. Oh, it was middle school? It's pretty middle school. Bye, guys.